lesson is compare and contrast the characteristics of fission and fusion reactions. So fission occurs when a large nucleus is split into two or more daughter nuclei. Now, with our Play-Doh simulation, we use, like nitrogen. Well, nitrogen is really not a large nucleus, but it wouldn't really has been as economical to sit there and roll out 238 balls for neutrons and protons, right? So we just use nitrogen because it would be easier to make it, but in reality, it only happens to large nucleuses, okay? Nuclei, there's no such thing. So fission, as we saw, requires a free neutron to collide with the larger nucleus. So that's what's happening, the collision when we drew the before and after, that neutron is coming in and hitting it. So if we looked at something like uranium, here we have the neutron coming in, and here's our uranium atom. So all of the little blue dots are our neutrons, and all of the red is our protons. So it comes in, and it has this kind of a intermediate stage, we could call it, where it's super unstable and the collision is happening. So the neutron comes in. It releases gamma rays as well. So here we can see these are gamma rays. So it's releasing a lot of energy during this reaction. And then here it says it makes a strontium 90 and xenon 143. So let's just look at adding up and making sure the conservation of charge is consistent here. So we have one neutron, so we have N is 1 and 0, plus our uranium, which is 235 and 92. This is going to produce 3 neutrons. So here in our example, there's 1, 2, 3. Plus our xenon 143 and 54. Plus our strontium 90 and 38. So let's just kind of look and see if that all adds up. So here on this side, for our protons and neutrons, we have 236, okay? And here we have 3 plus 143 is 146, plus 90 is what? 146 plus 90, that's like going plus 100 except minus 10. So that's like 230, oh, great. So check for that, cool. Now let's check our charges. So on this end we have 92, and here we have 54 plus 38 is 92. Excellent. So on the top, that was when we were doing conservation of nucleons, right? Nucleons means proton and neutron. And the bottom is conservation of charge, okay? So conservation of nucleons, conservation of charge. Next lesson that we do, we're going to be doing the last one, conservation of mass nucleons. That's Einstein's theory. That's the one that we'll do next. Okay, so then actually flip to your next page, and we'll fill in the compare chart for fission, since we just did that one. So you can flip to the back, just turn it over. So for fission, so the definition, fission is the splitting of a large atom into 2 or more smaller, so it could be multiple. Requirements for the reaction. The parament element needs a critical mass and a high-speed neutron. However, very little energy is required to split atoms in a fission reaction. So it's not a lot of incoming energy is needed, but except for that neutron moving at a high speed. Now, the energy released by fission is 1,000,000 times greater than released in just any chemical reaction. So when we're taking apart the atom, a lot of those gamma rays are released, which is an incredible amount of energy compared to just like an exothermic reaction, just giving off some heat. Okay, but it is still lower than the energy released by nuclear fusion. So if we compare fission to fusion, fission is still a lower amount of energy than the fusion is. This is going to be even bigger. So it's going to be like, this is the sun. This is like a nuclear bomb. Okay? So when you think about it that way, it's like, wow, the sun is really, there's lots of crazy stuff going on there. So natural occurrences. As Maddie had asked, fission does not occur in nature. It is a man-made reaction used in atomic bombs and nuclear power plants. Fission produces many radioactive particles, which can be very dangerous. Hence, that's why Chernobyl was so devastating, right? Because it was a nuclear power plant that, like, the situation happened, released, and so then all of that